Well, thank you for the introduction, and thank you for everyone making it to the last session of RosCon here. So this talk, again, is about bridging ROS to embedded systems. So we just heard the talk on micro ROS node. There'll be a talk after me about ROS-C. So this talk will take a different perspective. Instead of describing one approach in particular, I'm going to try to make a survey of the breadth of approaches that are out there. So instead of trying to, sell something or bash something else, I'm just going to try to look at what's out there, because oftentimes in embedded systems, their best method is going to be sort of driven by the application, whether you have a really extreme power budget or extreme performance requirements or something in between. So to start this talk, first, all robots have embedded systems. It's kind of one of the things that makes a robot, is there's oftentimes, or almost always really, a collection of smaller processors that then talk to analog sensors about the world, or to actuators to then affect the world. So it's not necessarily if we have these little embedded systems, it's rather how we're going to choose to talk to them. All robots have things like laser scanners, cameras, motors, radios. All these things have microcontrollers in them of some sort. Sometimes we have control over those devices, like we built them or we designed them. Like they were just describing in the previous talk, they have their own custom hardware nodes. Sometimes we don't. That's oftentimes the case if you're buying things off the shelf. Like when we buy a laser scanner, of course it has tons of internal firmware, but that's closed, that's proprietary to the company, so we can't, we have fewer options to play with there. But there's lots of situations, so that means there's going to be lots of valid approaches, which is what I want to survey here in this talk. So it's funny, even just the idea of embedded systems, if you ask 10 people what is an embedded system, you'll get probably 10 different responses. I'll just kind of go around the circle there, starting at the upper left. You can take a full ATX motherboard and put it in a box that doesn't look like a computer, and all of a sudden you can call it an embedded system. Oftentimes you see a large robot like the PR2, for example, and it has some x86 computers in there, but it's fair to call those embedded because there's not like a keyboard and a screen and kind of the usual things you associate with the computer. There are also smaller form factor motherboards and just everything in between. The center there, of course, is the most common kind of embedded system now. The smartphones, these things are amazing now. They're faster. I think, pretty sure the phone in my pocket is faster than my poor little netbook right here. They get cooler and more awesome every year. They are a classic definition of embedded system. It's an ARM A-class microcontroller, all tightened up into a nice package. It looks cool on the outside. So that's kind of the one class. The next class down would be the ARM A-class. So similar processor class, but without kind of the UI aspects to it. So like the Raspberry Pi there is sort of the bare bones of a computer without the UI. You sort of bring your own keyboard, or you bring your own TV or network or whatever. So the next class down below that is the ARM M class microcontroller, so Cortex M3 like they had in the previous talk, or other of these 32-bit microcontrollers. Now, these things are, that one in particular on the lower left there is the Embed platform. It's very popular, and these things are amazing. In quantity, these are like $1 or $2, these types of chips, and they're, just phenomenal. They run, 100 megahertz, 32-bit machine, on-chip flash and RAM and stuff. These are, I think it's fair to say, more powerful than the computers that many of us learned to program on, although I guess we're sort of dating ourselves there, but it's amazing what you can buy now. And then finally, on the lower right is the kind of entry-level type processor. This is the Arduino Mega. It has an AVR, an Atmel processor in it. That one's an 8-bit processor. They're extremely low power. So this is kind of a huge range of embedded systems. The lowest right there has extremely low power consumption, very simple to use. You basically just give that chip power and it can start blinking lights and doing fun things. All the way up to the upper left where we're taking 100 watts and can do amazing things. So it's a big range of things. So then if this is so big and complicated, why would we even want to embed things? The fantastic thing about embedded systems is you can kind of dial in exactly the kind of processing power and size that you need for your system, your goal. So you can then, if you're trying to make a product, you can minimize the cost, size, weight, power consumption, all that kind of stuff to give just the computation cycles that you need in your product. These are also becoming more powerful every year. I think that, of course, all computers get faster every year, but it seems to be more extreme. I don't know if the slope of the curve or whatever is faster in embedded systems, but it seems every year you go to the embedded show and they're like, oh yeah, it's been another year. Our thing is twice as fast and takes half the power this year. And you've sort of been hearing that for a long time. These market forces are massive. The number of embedded systems in the world dwarfs the number of personal computers in the world. They've, a couple years ago, they started selling more smartphones than PCs, and I'm sure now they sell more tablets than PCs also. So there's huge market forces making these things get better and better every year. And so with that, we can now do more and more on these systems. One of the things that I like to do, and some of the architectures I like to build, is that we can push a lot of the real-time requirements now down into the embedded systems. So now, rather than trying to have a full-size computer that's running both real-time and non-real-time code with some sort of hypervisor on top, we can instead put the real-time systems down into the embedded controller, which has sort of just enough power to do what it needs to do in real time. And then whatever is talking to that, whatever controller computer, can then be a non-real-time operating system, which oftentimes is a happier, friendlier programming environment. So to summarize these kind of popular hardware classes, I'll keep kind of referring back to these 4 throughout the talk. We have kind of in the upper left the x86 land, which is kind of, ROS does that really nicely right now with the binary package. You can buy one of these mini ITX motherboards that come from many vendors. You can just throw Debian or Ubuntu on there and start installing binary packages. The PC104 has been around forever, and it seems to sort of never die. They just kind of keep upgrading the processors, but the form factor stays the same. But it's the same thing. It's just an x86 machine. The ARM A class now, this is the Gumsticks, BeagleBone, Raspberry Pi type machines, as well as the smartphone, the Android world. That is, extremely popular. Raspberry Pi, I think, is like €40 or something like that, very cheap. Then coming down to the left, you have these, there's a whole bunch of these ARM M microcontrollers. There's the Embed, the STM32 Discovery. Sort of everybody that has a chip fab seems to make an ARM Cortex-M microcontroller. You can interface to them very easily now. There's all sorts of good open source tools. That's one that JTAG adapter there, that from AllMX is kind of my personal favorite. It's like $50 and easy to just connect to the whole open source tool chain. And then in front of the AVR world, we have the Arduino. There's, I don't know, maybe 10 different kinds of Arduinos in various sizes and shapes now. There's also other popular and different size platforms with Arduino, or sorry, with AVR. That's the Teensy is another kind of fun one, little tiny thing. So if we're talking about how we tie these things into ROS, there are massive disparities there of computational power. So there's kind of 2 extremes of how we're going to tie these systems. The one, I'll call it unified approach there, is kind of like the ROS Java, or like we do with the Android integration with ROS, where it's a first-class member of the ROS network. It can negotiate with the master. It can add nodes on itself. It can have more than one node on itself. It can then connect with all of its peers, just like anything would do on ROS CPP on a main large-scale x86 computer. Then there's sort of this fuzzy layer in the middle there's all sorts of different approaches in the middle, which I'll talk about. And then the other extreme is like, we'll call it bridged for now, which is you have a ROS network on top, all those little blue ROS nodes sending messages back and forth. And then there's kind of this gateway node, which we'll call a gateway or a bridge, which then translates all these messages into a different format, perhaps one that's easier to parse or more conservative with bandwidth, and then does point-to-point links out of there into, in this case, those 2 Arduino down there. So this is a spectrum, and so we'll talk more about what's in between here. So on the very top, the unified, we have kind of the prototypical ROS C++, ROS CPP, ROS Python, ROS Java for Android. And then as you come down, we have the ROS C project, which we'll hear talk from next about that, the micro ROS node we've just heard from. And then kind of now as we start to cross the gap into where things become more bridged, there's the ROS Bridge, which is actually amazingly applicable to a whole range of things. ROS Serial, which is more targeting the smaller end of things, and then the custom bridges, which are commonly done to target proprietary or otherwise unusual setups there on the lower right. So these ARM Cortex-A machines, and again, this is the like Raspberry Pi, Gumsticks, BeagleBone, smartphones, all that stuff. They can run all of ROS. Cross-compiling them it can be done. It is not for the faint of heart, but so I would say, if you're starting, definitely start with the binary distributions on Gumsticks there's the Linaro thing that they actually officially support now. Raspberry Pi that Rasby and Paul Matthew at OSRF was working for a long time over the summer, or his internship was to create these binary build farms for ARM, which I think has made a lot of progress. Now the next step down, we have the micro-ROS node and ROS-C. This is for these ARM Cortex-M microcontrollers. There's tons of these things. And as we saw in the previous talk, and I think we'll see on the next talk also, it is difficult because there's not a lot of RAM. These things almost always run just using on-chip SRAM. So you have a few tens of kilobytes, if you're lucky, maybe 100 or 200 kilobytes of SRAM on them. So you have to be clever, and as the micro-ROS node and ROS-C has done, where you have these code generators, so you say exactly what types of messages you're interested in receiving, then they generate code which can then handle that in a very memory efficient and space efficient way. And then as also the previous talk said, some of these platforms can then chain to other microcontrollers, either using Ethernet or other lighter weight or more deterministic transports there. So the thing that's exciting to me about this class of thing is just the price. You can literally buy these chips for $1 a piece and have a 32-bit machine running at 100 megahertz. It's really quite amazing. So now the ROS bridge we're talking here is a very interesting thing. So we heard a talk about it this morning, so I won't mean to summarize too much, but essentially you can take ROS messages flying all around, convert them into JSON, and then blast them out over sockets to wherever you want. So this morning there was a lot of demonstrations using web browsers, but also you could do that to really anything that can open a socket and transmit across it, which is just about anything. So we can have the links there to the ROS bridge. The topology kind of starts looking like where you have this kind of gateway, which is then retransmitting out to all sorts of other things. On the right side, those orange bubbles there, which can be microcontrollers, they could be web browsers or who knows what, maybe embedded Linux or real-time systems running different, running things that don't have anything to do with ROS at all. So ROS serial is a similar concept. The topology looks the same, except now instead of doing a socket, we're then slimming it down even closer to a serial stream, so you can then just blast it out a UART or some sort of a serialized packetized radio system like an XP. There are ports available there on the website for Arduino, it's a massively popular setup right now, and the generic embedded Linux that Paul Boucher has contributed so that it can talk with any kind of embedded system. Again, that doesn't have anything to do with ROS. So custom bridges, this is kind of, I think, probably the most common in terms of just day-to-day, you have a robot and you want to use it. Because all these widgets that we buy that come in shiny boxes, they're implementing firmware that usually we can't touch, which means that over on the ROS side, we now need to write a device driver to interpret whatever their firmware proprietary protocol is out into something that ROS can recognize and use. So for example, the Hokuyo laser drivers, and then a million other things, anything you buy, pretty much someone has to write a translator that will talk to that firmware. That crazy diagram on the bottom is for the Sandia Hand, which is a project that I'm working on right now. It's fully open sourced. All the firmware, software, everything you can download there at that link. But essentially I have a bunch of custom firmware down at the bottom there to make this microcontroller network all talk to each other. There's an FPGA that kind of unifies everything into a gigabit Ethernet UDP stream, and then blasts it up to a host, which then kind of cracks that apart and retransmits everything out as ROS messages. As part of doing that project, I've made a bunch of scripts. These may or may not be useful to people. They're all really well, they have plenty of issues, but I just thought I'd put them out there on the web anyway. This is the toolchain that I've used usually, GDB through an open source program called OpenOCD, which can tie some low-cost JTAG adapters back to Linux and down to your embedded target. And so then you get a GDB server and you can do stepping and watching and breakpoints and all that kind of fun stuff. That project there, I have scripts that will, essentially you just type make in the firmware directory and it will download a particular kind of a pegged version of ARM GCC, download and build up OpenOCD, and then it gives you rules for cross-compiling, for creating bootloaders and various things that I've done. So I didn't have a demo. I didn't bring any hardware, unfortunately, but this is the extent of my demo today. So you'll see that it's actually cross-compiling now, and it's kind of fun. I had to have some sort of a demo, some reason, that something could break to make it exciting. But looks like it's going there. So what it's doing now is building a bunch of libraries. This is all for ARM Cortex-M3 stuff, building a bunch of bootloaders for all the different parts of the system. So anyway, you can feel free to grab that stuff. If we want to make that more generic, if that actually turns out to be useful, we can definitely try to make that more general to other projects. Let's see, in the interest of time, I think I'll mention this a little bit. We also have, for this open source hand project, we have, there's a gigabit Ethernet physical layer that's in the bottom of the hand. And so I've done some work with some other friends to create a simulation environment for that. so that we do everything from the command line on Linux. The simulator is Icarus Verilog, which is a GPL Verilog simulator. Maybe some of you have used it. It's a great tool. And then we've adapted it so that there's a kind of an extra shim we can put in there so that the Ethernet in the simulation will actually bubble out as a virtual device to the Linux kernel. So you can then debug your driver all through simulation, which is kind of fun. But if that might be useful to some, if it is, please let me know. We can make it more generic. So just to acknowledge, this is all stuff that is available out there. We've discussed many of this on the ROS-SIG embedded user group on Google Groups. And this also comes, some of it, out of the ROS for Products workshop. There's, as you can see, just from kind of this survey of the scene here, there's a ton of stuff going on with the embedded world at all different levels. The embedded world is huge, and there's interesting things happening at all levels. There's a lot of interest in creating an ANSI library that will be bare metal as well as RTOS. So that's just kind of a segue for the next talk about ROS-C here. So thank you for your time.